Hello and welcome back to the Deep Dive. Before we jump into the architecture today, just a quick disclaimer. The content you're about to hear is AI generated based on authoritative sources.
And today we are digging into something really interesting.
Oh, we are. We're opening up the C++ archives to look at a data structure that I think occupies a very strange place in the engineer's psyche.
Oh, yeah.
It's a component everyone knows. Most performance engineers, let's be honest, actively despise, but very few actually understand the history of. We're talking about std.list.
The classic doubly linked list. And you're spot on about the reputation. In modern high-performance code, std.list is, well, it's the punchline of every optimization joke.
Right. If you see it in a code review, the knee-jerk reaction is just to flag it and say, use a std.vector.
Just use a vector every time.
It's the villain of the data-oriented design movement. But the mission for this deep dive isn't to bash a 30-year-old container. It's to understand the rationale.
Yes.
Because std.list wasn't designed to be slow. It was designed to be, in a way, mathematically perfect.
That is the absolute key. It's a masterclass in software architecture. The story of std.list is really the story of the tension between theoretical purity, these abstract mathematical sequences, and the gritty physical reality of the hardware.
So the core question we're exploring today is, why does std.list work the way it does? And how did the infamous memory wall turn this perfect abstraction into such a hardware bottleneck?
We're going to trace that whole arc from the HP Labs implementation back in the early 90s through the bureaucratic nightmare of C++11, all the way to the C++26 constexpr revolution.
Okay, let's start at the genesis. We're going back to the early 1990s. This is pre-standardization C++ year. We have Alexander Stepanov and Meng Li at Hewlett-Packard Laboratories.
Right, the birth of the STL. This is really where the whole philosophy of generic programming crystallizes.
And the timeline here is incredibly tight. They presented the library to the NCSO C++ committee in November 1993. By March 1994, Andrew Koenig is already requesting the formal proposal.
So std.list is born right in that specific window. And to get the design, you really have to get inside Stepanov's head. He wasn't thinking about cache lines or instruction pipelines.
Yeah, not at all.
He was thinking about sequences.
A pure mathematical concept.
Exactly. See, std.vector is fundamentally about arithmetic. It's base res plus offset. It's geometry. But std.list is topological.
Okay.
It's an ordering defined entirely by pointers. It introduced this whole concept of the bidirectional iterator.
Which brings us to the hardware context. In 1993, this topological approach, it wasn't a performance crime.
Not at all. The memory hierarchy was completely different. It was much, much flatter. The penalty for a cache miss, where the CPU has to go all the way out to main RAM, was so much lower relative to CPU cycles than it is today.
So chasing a pointer was just fine.
It was an acceptable trade-off for the algorithmic flexibility you got. And that flexibility was huge.
Stepanov and Li prioritized mutation over access, right?
Precisely. If you're just manipulating pointers, you can splice lists, you can sort them, merge them, all without ever copying the actual data objects. You're just rewiring the topology.
So what were those core design principles that got engineers in 1994 so excited?
Okay, so first, generic programming. It had to work with any copyable type. Second, value semantics. It holds values, not references. It does deep copies. But the third one, and this is the one that still matters today, is referential integrity.
Let's drill down on that. Referential integrity is the contract that std.vector just can't sign.
Correct. If you insert an element into the middle of a vector, everything to the right has to shift in memory to make room.
Which means their addresses change.
And any pointer you held to those elements is now arguably invalid. But in std.list, a node stays at a fixed memory address until you explicitly erase it.
So if I have a pointer to an element, I can trust that pointer, basically forever, no matter what happens to the rest of the list.
That was the guarantee. Iterators remain valid indefinitely. It was elegant, it was robust, and it was safe. It let you build systems where objects could reference each other without fear of the container pulling the rug out from under them.
But then, the silicon betrayed the abstraction. We entered the 2000s and we hit the memory wall.
And this is era one of our timeline, the fall from grace. The gap between how fast a CPU could think and how fast it could get data from RAM just started widening. drastically.
We started seeing the dominance of the CPU cache.
Exactly.
And for anyone listening who doesn't spend their days profiling code, we're talking about how modern CPUs fetch memory in chunks cache lines, usually 64 bytes at a time.
Precisely. And std.vector is contiguous. So if you ask for index 0, the hardware grabs index 0, but it also accidentally grabs index 1, 2, and 3 for free because they're sitting right next to it. That's spatial locality.
Plus, the hardware prefetchers, they're basically pattern matching engines. They see you reading 1, 2, 3.
And they go and speculatively fetch 4 and 5 for you.
But std.list is just totally hostile to this.
Completely hostile. Every node is allocated separately on the heap. So node A might be at address 1000, and node B, the very next node in the sequence, might be at address 9000.
The prefetcher has no chance. It's just random access.
It's what we call pointer chasing. The CPU gets the first node, reads the pointer to the next one, and then it just waits. It stalls. It literally stops and waits for hundreds of cycles to fetch that next random address. It completely breaks the instruction pipeline.
And this is what Bjarne Stroustrup famously showed in his Going Native 2012 Keynote. That was a huge moment for a lot of C++ developers.
It really was. He showed that std.vector actually outperforms std.list, even for insertion.
Yeah.
Which is supposed to be the one thing a list is good at.
That's the part that feels so counterintuitive. Logically, shifting elements in a vector sounds slow. std.list insertion is just swapping 2 pointers. That should be instant.
It is instant, but only once you're at the insertion point. The problem is getting there. Traversing the list just to find the spot takes so long because of all those cache misses that the vector wins by brute force. Plus, a move on contiguous memory is just blazing fast.
And we haven't even touched the space penalty.
Oh, it's massive. On a 64-bit machine, a pointer is 8 bytes. A doubly linked list needs a next and a prev pointer.
So that's 16 bytes of metadata per element.
Right, so if you're storing a simple 4-byte integer...
So you're paying 16 bytes of overhead for 4 bytes of data. That's a 400% space penalty.
It's incredibly inefficient for small data types.
So by the late 2000s, the hardware had turned against the design, but the software side was having its own drama. Which brings us to era 2, the C++11 complexity pivot. This is where it gets bureaucratic.
This is the era of the great size debate. It really peaked around 2009.
I remember this vaguely. It was about whether list.size should be constant time O1 or linear time ON, right?
Exactly. In C++98, the standard was ambiguous. It actually allowed size to be ON, which meant the list had to count every single element one by one every time you asked.
That seems absurd for a container. Why would anyone want a linear time size check?
To allow for O1 splicing, this is the trade-off. If you want to take a subrange of element from list A and move them to list B, and you don't store the size, you just change a few pointers at the boundaries. It's instant.
Ah, but if you have to maintain the size...
Then every time you do that splice, you have to count how many elements you moved, update the size variable for both lists. So you could have fast splicing or fast sizing, but not both.
And in 2009, proposal N2923 from Alan Talbot and Howard Hinnant argued that the status quo was dangerous.
They argued from the principle of least surprise. Developers just assume size is a fast check. People were writing code, like if list.size 0, thinking it was cheap.
But on some implementations, like GCC at the time, that one line of code was triggering a full traversal of the entire list.
A huge hidden performance footgun. So the proposal was simple. Mandate O1 size.
And they decided that users check the size way more often than they splice subranges.
Yes, so C++11 mandated that size must be constant time, which effectively killed the O1 range splice.
Specifically the range splice, right? Not the whole list.
Right, that's a key distinction. Moving elements 5 through 10 from one list to another became ON. But splicing an entire list from one to another could stay O1, because you already know the size of the source list.
That seems like a logical decision optimized for the common case, but it caused this massive headache for implementers. This is era 3, the ABI crisis.
It was a total nightmare, especially for the GCC team. Because to make size O1, they had to add a member variable to the class. They std.size it to store the size.
Which changes size of std.list, the object gets physically bigger on the stack.
And that breaks the application binary interface, the ABI. If you have a library compiled with the old C++98 std.list and an application compiled with the new C++11 std.list.
And they try to pass a list object between them.
You get memory corruption. The app tries to read a size variable that the library never wrote. Undefined behavior. Crashes.
So GCC just didn't comply for a while.
For a while, yeah.
Go.
GCC Fort Worth X kept size
Huh.
as ON because they prioritized binary compatibility over strict standards compliance.
So how did they finally solve this? This is the famous Dual ABI solution, right?
It took until GCC 5.1. They used this really clever namespace trick. They created an inline namespace called std.cxi11.list.
So mechanically, how does that work?
When you compile your code and include list, the compiler checks your settings. If you're compiling for the new ABI, std.list actually resolves to std.cxi11.list. If you're using the old ABI, it just resolves to the old std.list.
So the linker ends up seeing two completely different stools.
Exactly. Legacy code links against the old ON list, new code links against new O1 list. They can coexist in the same program, but, and this is key, they cannot interoperate. You can't pass one to a function expecting the other.
That's wild, that a simple decision like make size fast resulted in years of architectural workarounds and symbol versioning.
It's the nature of standardizing a language that's used by millions. Every single byte matters, and backward compatibility is a straitjacket.
So, okay, we've established that std.list is slow for traversal, has memory overhead, and caused ABI headaches. This raises the question a lot of engineers, especially in game dev, ask, why don't we just use intrusive lists?
Great question. In game engines or in kernels, like the Linux kernel, you almost always see intrusive lists. That's where the next and prev pointers are embedded directly inside the object itself.
Right, you inherit from some kind of link node struct.
Exactly, which means zero allocation overhead for the node and way better cache locality because the pointers are right there with the data.
So why did the C++ committee reject that approach for the standard?
Two big reasons. Safety and generosity. The committee prioritizes value semantics and RAII resource acquisition, is initialization. With an intrusive list, memory management is all on you.
If I delete the object but forget to unlink it from the list?
You've got a dangling pointer and a corrupted list. std.list manages the lifetime of the node for you. And then there's the generic case. You can't put intrusive pointers inside a primitive type like an int.
Ah, right, you can't do struct in a .public list node.
Exactly. The STL has to work for everything, primitives included.
Fair enough. But they did try to offer a lighter alternative in C++11, std.forwardList.
Yes, proposal N2543. The singly linked list. This was the zero overhead compromise. They wanted a container that was physically identical to a hand-rolled C-style linked list.
Just a pointer and a value.
And to get there, they had to be ruthless. std.forwardList does not have a size member.
Because storing the size would cost extra memory.
Correct. Size of std.forwardList is exactly equal to size of void. It's nothing but a head pointer. And because it's singly linked, you can't go backwards. There's no insert or erase. You only get insert after and erase after.
So we've got vector for speed, forward list for pure space efficiency. What keeps std.list in the standard? What's its killer feature?
Iterator invalidation guarantees. That's the one thing std.vector cannot do.
And this is so crucial for certain architectures. Walk us through the classic event system example.
Okay, imagine you have a list of listeners or observers for an event. You're iterating through that list to notify them. Now, what if one of those listeners decides, okay, I'm done, remove me from the list?
If I'm using a vector, removing that element shifts everyone else down to fill the gap.
And your iterator, the very thing keeping track of where you are in the loop, is now invalid. It's pointing to the wrong thing or even off the end. Your loop crashes or it skips the next listener. It's a disaster.
But with std.list,
You can remove the current node you're on, and the iterators pointing to all the other nodes remain perfectly valid. They are stable. This referential stability is why std.list is still the right choice for things like handle systems or observer patterns where objects need to manage their own membership.
so it's not about data processing speed, it's about structural stability.
Precisely. It enables a specific kind of decoupled architecture.
Okay, let's look at the modern era. C++17 to C++26. Is std.list just a fossil, or is it evolving?
It's evolving in really fascinating ways. C++17 gave us PMR polymorphic memory resources. So you have std.pmr.list.
That lets us control the allocation strategy.
Exactly. You can use something like a monotonic buffer resource. You basically allocate one big chunk of memory up front, and then the list nodes are carved out of that single block.
So the nodes end up physically close together in RAM, which helps the spatial locality problem.
And improves it significantly. You're not hopping all over the heap anymore. But You still have the pointer structure. The CPU still has to load a pointer to find the next address. So it helps, but it doesn't cure the fundamental pipeline stall.
C+20 gave us a nice little usability fix remove, finally returns the count of elements removed instead of void. But the real story is the constexpr revolution.
This is where it gets a little bit sci-fi. C++20 allowed new and delete in constexpr contexts, so at compile time. As long as you free the memory before the constant expression ends, you can use dynamic allocation during compilation.
And C++26 is pushing this even further with proposal P2747.
Right, allowing placement new in constexpr and P2738 for casting void. What this all means is that std.list is transforming into a meta-programming tool.
Wait, you mean I could use the std.list inside the compiler?
Exactly. You could use the std.list to manipulate complex sequences of data, sort them, splice them, reorganize them all while the compiler is building your program. Then at the end, you generate a static, perfectly optimized data structure for the final binary.
So the linked list could make a comeback not in our RAM at runtime, but inside the compiler's memory while it's building.
It returns to its roots as a pure abstraction for sequence manipulation, totally unburdened by runtime hardware constraints. Inside the compiler, the memory wall doesn't matter in the same way.
That is a beautiful full circle. So let's synthesize this for everyone listening. What's the final verdict?
I think the summary is that std.list is not a bad container. It's a precision scalpel. It was just optimized for a machine model that, for high-performance code, no longer exists.
Zero overhead is relative to the hardware you're on.
The abstraction didn't change, the silicon did.
So for the staff engineers and tech leads listening, what's the actionable takeaway?
Default to std.vector 99% of the time. If you need a FIFO queue, use std.beak. But use std.list when you specifically need that referential stability, when pointers to elements absolutely must never move, or if you're splicing entire lists together and want to avoid copies.
It's a specialized tool for a specialized job. Don't use it for cache performance. Use it for its architectural guarantees.
Exactly. And don't just blindly follow best practices without understanding the historical context for why they exist in the first place.
I like that. It's a great reminder that our code is always a negotiation with the hardware. Before we go, here's a provocative thought to leave you with.
Okay.
With C++26 allowing these complex data structures at compile time, are we about to see a renaissance of linked lists? Not running on your server, but running inside your build pipeline to optimize your binary before it even exists.
That is a very real possibility. The list might be dead in the cache, but it's very much alive in the compiler.
Something to mull over. Thank you for joining us on this deep dive into std.list. We'll catch you on the next one.